November 16, 1944, somewhere along the Siegfried Line near Aachen, Germany. A Sherman tank of the 3rd Armoured Division sits motionless in the mud, its tracks spinning uselessly, throwing up fountains of brown water that arc 20 feet into the grey morning air. Inside, 5 men wait to die. The tank isn't stuck on a mine. It hasn't been hit by an 88. It's simply sunk too deep into the saturated earth to move. And every tank crewman in Europe knows what happens next. German anti-tank teams are already moving into position, taking their time, because this Sherman isn't going anywhere. The crew has maybe 5 minutes before a Panzerfaust rocket turns their steel coffin into an incinerator. This is the autumn of 1944, and American armour is drowning. Not in a single dramatic battle, but in thousands of identical moments across Belgium, Holland, and Western Germany. Shermans designed to race across open terrain are instead grinding to helpless halts in the wettest European autumn on record. And when a tank stops moving in combat, it becomes a target. When it becomes a target, it burns. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mathematics of the crisis were brutal and undeniable. Between mid-September and late November of 1944, American armoured divisions were losing tanks to mud almost as fast as they were losing them to enemy fire. Combat reports from the First Army documented the pattern with grim repetition. A tank column would advance down a muddy road. The lead Sherman would break through the surface crust and sink to its belly. Crews would attempt to reverse out. The spinning tracks would only dig deeper. Within minutes, the entire column would be stalled, bunched up, unable to maneuver, presenting perfect targets for German gunners positioned on the surrounding high ground. The 3rd Armoured Division's official history recorded that November 16th became one of the most critical days in their campaign, not because of German counterattacks or Tiger tanks, but because of the weather and the ground itself. Staff Sergeant Belton Cooper, serving with the division's maintenance battalion, watched tanks disappear into the mud with a horror that exceeded anything he'd witnessed in Normandy. The soft ground would mire the tank so deeply that it would stick, he wrote in his combat diary. All the stuck tanks became sitting ducks for the murderous German anti-tank fire. The autumn of 1944 was the wettest on record in northwest Europe. Rainfall totals exceeded normal levels by more than 200%. Rivers swelled beyond their banks. Agricultural fields that should have been solid enough to support tracked vehicles transformed into liquid mud pits feet deep. And the American Sherman tank, brilliant in so many ways, had a fatal flaw that made it uniquely vulnerable to these conditions. Its tracks were too narrow. The standard Sherman, whether the M4A1, M4A2, or M4A3 model, rolled on vertical volute spring suspension with tracks measuring just 16.5 inches wide. This created a ground pressure of approximately 14.3 pounds per square inch when the tank weighed its standard 33 tons. In dry conditions, on hard ground, this was adequate. In the bottomless mud of Belgium in November, it was catastrophic. German intelligence reports from late 1944 noted the American armor's difficulties with satisfaction. Captured documents reveal that Wehrmacht commanders specifically ordered defensive positions established in low-lying waterlogged terrain, knowing that American tanks would struggle to maneuver. The Germans understood what American planners had failed to anticipate. Narrow tracks meant Shermans would sink. Sinking tanks meant immobilized targets. Immobilized targets meant dead crews. The problem wasn't new. Soviet tankers using Lend-Lease Shermans on the Eastern Front had complained about track width since 1943. British units in Italy had filed reports about Sherman mobility in mud throughout the winter campaigns. But the issue reached critical mass in northwest Europe in the autumn of 1944 because of 3 converging factors. First, the scale. Hundreds of thousands of American soldiers were now engaged in sustained offensive operations across a broad front from Switzerland to the North Sea. Second, the terrain. The Low Countries and the approaches to the Rhine were fundamentally different from the relatively dry conditions of Normandy in summer. Third, the timing. The Allied advance had outrun its logistical tail. There was no time to wait for better weather. no opportunity to consolidate positions and prepare properly. The offensive had to continue, mud or no mud, because stopping meant giving Germany time to rebuild its shattered armies. Tank crews understood the danger viscerally. When a Sherman sank to its belly in mud, the engine would roar at maximum RPM, tracks would churn desperately, but the tank simply wouldn't move. Crews called it being bellied or bogged. The official term was mired. Whatever the terminology, the result was the same. You sat there, helpless, waiting for the anti-tank round that would end everything. Statistics from November 1944 paint the picture in blood and burning steel. The First Army reported that during the assault on the Siegfried Line between November 16th and 20th, over 100 Shermans were lost. Of these, approximately 40% were attributed to becoming mired in mud and subsequently destroyed by enemy fire. The tanks didn't fail mechanically. They didn't run out of fuel. They simply sank into the earth and couldn't get out. Crew casualties reflected the horror of immobility. When a tank was moving, when it could maneuver and return fire, crew survival rates after a penetrating hit averaged around 60%. When a tank was stuck, unable to move, that survival rate dropped to below 30%. German gunners could take their time, aim carefully, and punch holes through the Sherman's thinner side and rear armor. Crews trying to bail out of a stationary tank found themselves trapped by mud that was waist-deep surrounding their vehicle. The human cost extended beyond the immediate casualties. Tank units were experiencing psychological collapse. Replacement crews were arriving from training depots in the United States, being assigned to tanks, rolling forward into combat, and dying within 48 hours because their Sherman got stuck in the mud. Veterans who had survived Normandy and the breakout were watching friends burn in immobilized tanks and beginning to refuse to mount up for missions. Commanders at every level understood they were facing a crisis that threatened the entire autumn offensive. General Omar Bradley, commanding the 12th Army Group, received daily reports of tank losses that should have been categorized as non-combat, but were resulting in crew deaths just as surely as enemy fire. General Courtney Hodges, commanding 1st Army, watched his armoured spearheads grind to literal halts in the Belgian mud, and knew that if he couldn't restore mobility to his tanks, the drive into Germany would fail. The Ordnance Department, responsible for tank development and modification, was aware of the track width problem. Engineers at the Aberdeen Proving Ground in Maryland had been conducting mobility tests since early 1944. They knew that wider tracks reduced ground pressure and improved flotation in soft terrain. They had developed solutions. The horizontal volute spring suspension system, which increased track width to 23 inches, had entered production in August of 1944, but HVSS-equipped Shermans wouldn't reach Europe in significant numbers until December. The first HVSS tanks that did arrive went to newly formed units, or served as replacements for completely destroyed vehicles. The hundreds of existing Sherman tanks already in Europe, the ones with crews who had months of combat experience, the vehicles that formed the backbone of every armoured division, were stuck with their original narrow tracks, and those narrow tracks were killing their crews. The solution, when it emerged, didn't come from Aberdeen Proving Ground or from the Ordnance Department or from any official engineering study. It came from maintenance battalions scattered across France, Belgium, and Holland. It came from mechanics who were watching tanks return from the front line covered in mud, from recovery crews who were spending hours extracting bogged Shermans under enemy fire, from men who understood that the official solution was months away and their friends were dying today. The extended end connector was mechanically simple. Take a standard track end connector, the part that joins one track link to the next. Weld a flat steel plate approximately 4 inches wide onto the outer edge of that connector. Bolt the modified connector onto the track. The steel extension increases the track's effective width from 16.5 inches to approximately 20 inches. Ground pressure drops from 14.3 psi to around 11.5 psi. The tank's flotation in soft terrain improves dramatically. The idea wasn't revolutionary. German tank designers had used wide tracks on the Tiger and Panther specifically to reduce ground pressure. Soviet engineers had given the T-34 tracks nearly 20 inches wide. Even American engineers knew that wider was better. But implementing the modification required violating fundamental principles of military procurement and maintenance procedures. U.S. Army regulations explicitly forbade unauthorized modifications to combat equipment. Tanks were manufactured to precise specifications at approved facilities. Field mechanics were authorized to perform repairs according to technical manuals, but they were not authorized to alter the basic design of the vehicle. Extended end connectors weren't in any technical manual. They hadn't been tested at Aberdeen Proving Ground. They hadn't been approved by the Ordnance Department. Installing them was, technically, a court-martial offence. But in November of 1944, scattered across dozens of field maintenance companies, mechanics started welding steel plates onto track connectors anyway. They did it because the alternative was watching Shermans sink into the mud and burn. They did it because official channels moved at the speed of bureaucracy, while combat moved at the speed of death. They did it because sometimes survival requires breaking the rules. The first documented use of field-modified extended-end connectors appears in maintenance logs from the 2nd Armoured Division in mid-October 1944. The logs don't record who first had the idea or which specific maintenance company first implemented it. What the logs do show is that once the modification appeared, it spread with viral speed through informal networks of mechanics who talked to each other, who visited other units' maintenance areas, who saw what worked and copied it immediately. By early November, multiple armoured divisions were installing locally fabricated extended-end connectors. The modifications were crude. Maintenance companies would scavenge sheet steel from knocked-out vehicles, from German fortifications, from abandoned buildings. Mechanics would cut the steel into roughly rectangular plates using acetylene torches. Welders would attach the plates to standard end connectors using whatever welding equipment was available in field conditions. The finished products looked rough, with irregular welds and mismatched steel thicknesses, but they worked. Testing happened in combat. A Sherman with extended end connectors would roll forward through mud that had previously stopped tanks. The crew would report back that they'd crossed terrain that was impassable before. Other units would hear about this and request the modification for their own tanks. Maintenance companies would work through the night, welding extensions onto hundreds of track connectors per tank, racing against the next day's combat operations. The modification's effectiveness was immediate and measurable. Shermans with extended end connectors could traverse muddy fields that bogged down standard Shermans. They could maintain formation instead of spreading out to find solid ground. They could support infantry advances that would have been impossible with immobilized armor. Tank recovery operations that previously required multiple vehicles and hours of work could be completed in minutes because the stuck tank could power itself out with wider tracks, providing better purchase. Crew morale improved visibly. Tankers, who had been approaching every mission with fatalistic resignation, started showing confidence again. The modification didn't make them invulnerable. German anti-tank weapons could still kill them. But it removed the helpless terror of sitting immobilized in the mud while enemy gunners lined up their shots. By mid-November, the extended-end connector modification was spreading through the European theatre faster than any official program in military history. Maintenance battalions were installing them on Shermans at a rate of dozens per day. Tank crews were specifically requesting assignment to vehicles with the modifications. Combat reports were documenting clear improvements in mobility and survivability, yet the modification remained technically unauthorized. The Ordnance Department learned about the extended-end connectors through official channels in late October. Initial reaction from staff officers in Paris and rear area logistics centers was negative. The modifications violated procedures. They created non-standard configurations that complicated maintenance planning. They used unspecified steel that hadn't been tested for fatigue resistance. Most importantly, they established a precedent where field units could modify equipment based on their own judgment rather than following approved procedures. These were legitimate concerns in a peacetime military or even in a static defensive situation. But in November 1944, with the autumn offensive stalling in the mud and American casualties mounting, procedural correctness seemed irrelevant compared to combat effectiveness. Tank crews didn't care about procurement regulations. They cared about whether their Sherman could move through mud without becoming a sitting target. The disconnect between battlefield reality and institutional procedure created an extraordinary situation. Thousands of tanks were receiving modifications that the army officially disapproved of, yet no one in authority was ordering the modifications to stop. Company-level commanders knew their tanks needed wider tracks. Battalion commanders weren't going to discipline maintenance crews for keeping tanks mobile. Division commanders were watching their combat power increase and weren't asking uncomfortable questions about where the track extensions came from. Lieutenant Colonel Belton Cooper, whose maintenance battalion supported the 3rd Armored Division's tank operations, documented the modifications spread in his wartime journals. He described mechanics working in freezing rain, welding steel plates onto track connectors by the dim light of blackout lamps, racing to complete modifications before the next day's combat operations. The work was exhausting, technically demanding, and absolutely essential. Without extended end connectors, Cooper noted, many tanks would have been completely unusable in the November mud. The breakthrough moment came in late November, when General George Patton's Third Army entered the picture. Patton was preparing for his dramatic relief of Bastogne during what would become the Battle of the Bulge. His 4th Armoured Division would have to cover over 100 miles through snow and mud to reach the besieged town. Patton understood immediately that standard Shermans couldn't make that march. He needed every possible advantage. Patton's staff officers investigated the extended end connector modifications being used by other units. They reviewed combat reports showing improved mobility. They talked to tank crews who praised the modifications. Patton made a characteristically blunt decision. Every Sherman in 3rd Army would receive extended end connectors, official approval or not. If the Ordnance Department didn't like it, they could court-martial him after he won the war. 3rd Army maintenance battalions went into overdrive. They established assembly line procedures for installing extended end connectors. Steel was requisitioned from French contractors who were already producing the extensions as word of the modifications spread. By early December, 3rd Army had modified hundreds of Shermans, creating the most mobile armoured force on the Western Front at precisely the moment when that mobility would prove decisive. The relief of Bastogne validated Patton's judgment and effectively ended any official resistance to the extended end connector modification. When 4th Armoured Division's tanks rolled through snow and mud that should have been impassable, covering distances that German defenders thought impossible for mechanized forces, the value of wider tracks became undeniable. Combat reports from the Bastogne operation specifically noted that extended end connectors had been essential to the operation's success. But the real story of extended end connectors wasn't about generals or official programs. It was about hundreds of anonymous mechanics who saw a problem, developed a solution, and implemented it without asking permission. It was about field-level innovation driven by necessity, spreading through informal networks faster than any bureaucracy could move. It was about the moment when survival trumped procedure, and the army, despite itself, became more effective as a result. The contrast with official development programs was stark and instructive. The HVSS suspension system, which also provided wider tracks, had been under development since 1942. It went through extensive testing at Aberdeen Proving Ground. Engineering teams spent months refining the design. Procurement officers ensured that production facilities could manufacture the components to exact specifications. The first HVSS tanks reached Europe in December 1944, more than 2 years after development began. Extended end connectors, by contrast, went from initial field modification to theatre-wide adoption in approximately 6 weeks. No testing phase, no engineering review, no procurement contracts, just mechanics with welding torches, steel scrap, and the understanding that their friends were dying because tanks couldn't move through mud. The bureaucratic implications were profound and uncomfortable for an organization built on hierarchy and standardization. If field units could successfully modify their own equipment, what did that say about the official development process? If unauthorized modifications proved more effective than approved designs, what did that imply about the Army's engineering priorities? If mechanics could solve problems that stumped professional engineers, What did that reveal about the gap between theory and combat reality? These questions would echo through post-war military reform efforts. But in November and December of 1944, as American armor ground forward through the worst European winter in decades, the only question that mattered was whether the tanks could move. Extended end connectors ensured they could. Everything else was just paperwork. The modifications spread accelerated through December as the Battle of the Bulge demonstrated its value conclusively. Units that had extended end connectors maintained better formation integrity, responded faster to changing tactical situations, and suffered fewer losses to immobilization than units still using standard tracks. After-action reports from the Ardennes offensive documented cases where Shermans with extended end connectors successfully maneuvered through terrain that German intelligence had assessed as impassable to armor. By January of 1945, the extended end connector had achieved something remarkable. It had become standard equipment without ever receiving official approval. Maintenance companies treated it as routine procedure. Replacement tanks arriving from depots were immediately modified upon reaching forward units. Even the Ordnance Department, which had initially opposed the unauthorized modifications, quietly began ensuring that maintenance units had adequate supplies of suitable steel for fabricating extensions. The final official recognition came almost as an afterthought. In March 1945, as the war in Europe entered its final months, the Ordnance Department issued a memorandum acknowledging extended end connectors as an authorized theater-specific modification. The memorandum came with detailed specifications for construction, welding procedures, and installation. It was, in effect, the Army catching up to what its own mechanics had already accomplished months earlier. The specifications were largely ignored. Field mechanics had their own methods that worked, their own sources of steel, their own welding procedures refined through months of practical experience. The official memo simply formalized what had already become established practice. It was bureaucracy's way of pretending it had been in control all along. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps. Let us continue producing in-depth content like this. The engineering behind extended end connectors was deceptively straightforward, but understanding why they worked requires examining the physics of armored vehicles operating in saturated soil. A Sherman tank weighing 33 tons distributed across tracks 16.5 inches wide created approximately 14.3 pounds per square inch of ground pressure. This number becomes critical when you understand soil mechanics. Dry, compacted soil can typically support pressures exceeding 20 psi before deformation occurs. Wet clay, the dominant soil type across Belgium and the Netherlands, loses structural integrity dramatically when saturated. Tests conducted by Army engineers in late 1944 found that waterlogged Belgian clay could support only 10 to 12 psi before experiencing catastrophic bearing failure. A standard Sherman exceeded this threshold by 20 to 40%, which meant the tank would sink until enough soil displaced to create additional resistance. The mathematics of extended end connectors changed this calculation fundamentally. Increasing track width from 16.5 inches to 20 inches increased the contact surface area by approximately 21%. This distributed the tank's weight across more soil, reducing ground pressure to 11.4 psi. Suddenly, Shermans could operate within the bearing capacity of saturated clay instead of exceeding it. But the modification's benefits extended beyond simple flotation. Wider tracks also provided more surface area for traction. When a Sherman's tracks spun in mud, narrower tracks would simply dig deeper, creating a self-perpetuating problem where the tank sank as it tried to escape. Wider tracks distributed the rotational force across more surface area, allowing the tank to gain purchase on firmer soil layers below the saturated surface. The materials used for extended end connectors varied, wildly depending on what maintenance companies could scavenge. The ideal material was mild steel plate, approximately 1/4 inch thick. This provided adequate strength without adding excessive weight, but in practice, mechanics used whatever steel they could find. Salvaged armor plate from knocked-out vehicles, structural steel from destroyed bridges, sheet metal from abandoned German fortifications. Even railroad track, cut and hammered flat. The inconsistency created its own problems. Steel that was too thin would bend under stress, reducing effectiveness. Steel that was too thick added weight without proportional benefit, and put additional strain on the tank's final drive and transmission. Mechanics learned through trial and error, developing an intuitive sense for what worked. A good extended-end connector should be rigid enough not to deform under normal operation, but flexible enough to absorb impact stress without fracturing. Welding procedures varied just as widely. The official Ordnance Department specifications, when they finally appeared in March 1945, called for continuous bead welds along the full length of the attachment interface. But field mechanics rarely had time or resources for such careful work. Instead, they used tack welding, spot welding at intervals, or whatever method could be completed quickly with available equipment. The question became whether these rough field modifications would survive combat conditions. Extended-end connectors faced extraordinary mechanical stress. Each rotation of the track subjected them to impact forces as the track links engaged the drive sprocket and idler wheel. Uneven terrain created lateral stresses. Turning movements put torsional loads on the extensions, and all of this occurred in an environment of mud, water, and occasional enemy fire. The answer, confirmed through months of combat use, was that even crude extended-end connectors proved remarkably durable. Yes, extensions broke off, but occasionally. Yes, poorly welded units sometimes failed after a few days of operation, but the failure rate remained acceptable because the extensions were easy to replace. A maintenance crew could remove a failed extended-end connector and weld on a replacement in under an hour. Compare this to the days or weeks required to replace damaged suspension components or install HVSS systems. This ease of replacement became one of the modification's key advantages. In combat, simplicity and speed often mattered more than perfection. A Sherman with a few broken extended-end connectors was still more mobile than a Sherman with none, and if an extension failed completely, the tank could continue operating on standard tracks until the next maintenance opportunity. The human dimension of implementing extended-end connectors reveals the extraordinary competence and initiative of American maintenance personnel. These weren't engineers with advanced degrees. They were mechanics, welders, and metalworkers, many of whom had been farmers, factory workers, or shop technicians in civilian life. They'd received technical training, but nothing in their curriculum covered designing and implementing field modifications to improve tank mobility. Yet they did exactly that, working with remarkable sophistication. Maintenance companies established quality control procedures. Senior mechanics would inspect completed installations, checking weld integrity and alignment. Units developed standardized patterns for which track links should receive extensions and which should remain standard. Some companies experimented with installing extensions on alternating links to save weight while maintaining improved flotation. The work happened under conditions that would be considered impossible in any peacetime context. Mechanics welded in freezing rain, in darkness, often within range of German artillery. They worked on tanks that were still crusted with mud from the previous day's combat, engines, barely cooled, crews sleeping nearby in exhausted stupor. They worked knowing that their modifications would be tested in combat within hours, that defective work could result in crew deaths, that there was no second chance to get it right. Staff Sergeant James Bennett, serving with the 2nd Armoured Division's Maintenance Battalion, kept a detailed journal throughout the autumn of 1944. His entries from November provide insight into the practical challenges of implementing extended-end connectors at scale. On November 18th, he recorded that his maintenance company completed modifications on 23 Shermans in a single overnight session. The work required approximately 250 extended-end connectors, all of which had to be fabricated from salvaged steel. Bennett described the process methodically. First, steel scavenging teams would locate suitable material. German pillboxes in the Siegfried Line proved excellent sources, their structural steel already cut to convenient sizes. Second, cutting teams would use acetylene torches to section the steel into plates roughly 4 inches wide and 12 to 16 inches long. Third, Welding teams would attach these plates to standard track-end connectors removed from supply stocks. The assembly line approach worked because maintenance battalions had learned organizational efficiency through months of combat experience. Different specialists focused on different tasks. The best welders handled the critical attachment work. Less experienced personnel managed material handling and quality control. Officers coordinated with combat units to schedule which tanks would be modified when, ensuring that modifications didn't reduce the number of operational vehicles at any given time. Bennett's journal also documented failures and problems. On November 21st, he noted that 7 extended-end connectors had failed on a single tank during combat operations. Investigation revealed that the welding crew had been rushed and had used inadequate penetration on their welds. The tank crew had survived because the remaining extensions provided enough improved mobility to extract the vehicle from a potentially lethal situation, but the incident emphasized the importance of quality work even under time pressure. The French connection to extended-end connector production represents one of the war's lesser-known industrial collaborations. As word of the modification spread through maintenance channels in November, demand quickly exceeded what field units could produce through scavenging and improvisation. Someone, and the historical record doesn't clearly identify who, realized that small French metalworking shops could manufacture extended-end connectors far more efficiently than maintenance battalions welding them by hand. By December 1944, dozens of small factories across liberated France were under contract to produce extended-end connectors. These weren't major industrial facilities, but rather local workshops that before the war had manufactured agricultural equipment, construction materials, or consumer goods. Now they were cutting steel plate, drilling bolt holes, and shipping finished extended-end connectors to American maintenance depots. The French manufactured units showed notable quality improvements over field-fabricated versions. Professional metalworkers using proper machine tools could achieve more consistent dimensions, cleaner cuts, and more precise hole placement. The standardization mattered because it reduced the time required for installation and improved interchangeability between different track types. Production numbers remain unclear because the contracts were arranged informally and often involved payment in kind rather than currency. American logistics officers would provide raw, steel, and sometimes welding supplies. French factories would return finished extended-end connectors. The arrangement worked because both parties had strong incentives for success. Americans needed wider tracks. French factories needed work and resources in a still devastated economy. By January 1945, French production had reached a scale where extended-end connectors were readily available through normal supply channels. Maintenance units could requisition them like any other spare part. The modification that had started as an unauthorized field improvisation had become integrated into the theatre's logistical infrastructure, all without formal procurement contracts or official approval. The combat validation of extended-end connectors played out across thousands of individual engagements throughout December 1944 and January 1945. The Battle of the Bulge provided the most dramatic demonstration, but the modification's value was confirmed daily in less publicized actions across the entire Western Front. Combat reports from 4th Armored Division's drive to relieve Bastogne provide specific examples. On December 22nd, the division's lead combat command encountered a series of stream crossings, where the approaches had been churned into deep mud by previous military traffic. Standard Shermans would have required extensive preparation, possibly bridging or corduroy roads built from logs. Shermans with extended-end connectors crossed with minimal delay, maintaining the speed that made the relief operation possible. Lieutenant Colonel Creighton Abrams, commanding 37th Tank Battalion in 4th Armored Division, specifically credited extended-end connectors in his after-action report. His battalion's tanks had been modified in late November, using a combination of field-welded and French-manufactured extensions. During the Bastogne operation, Abrams noted that his unit maintained formation integrity better than previously possible in winter conditions, allowing more effective combined arms operations with supporting infantry. The psychological impact on German defenders proved significant and unexpected. German defensive planning had relied heavily on terrain analysis, showing that American armor couldn't maneuver effectively in winter conditions. When Shermans appeared in locations that German intelligence had assessed as impassable to vehicles, it created tactical surprise that American commanders exploited ruthlessly. Defenders positioned to cover likely approaches found themselves outflanked by armor, advancing through supposedly unusable terrain. Captured German officers, interrogated in January 1945, expressed genuine confusion about American tank mobility. Several specifically mentioned that Shermans seemed to have wider tracks than before and asked whether new tank models had been introduced. When informed that the modifications were simply bolt-on extensions rather than new vehicles, some German officers expressed frustration that such a simple solution had been so effective. The extended track width also provided secondary benefits that hadn't been initially anticipated. The wider footprint improved stability on side slopes, allowing Shermans to traverse hillsides that would have risked tipping with narrower tracks. Obstacle crossing improved because the tank's weight was distributed more effectively across the leading edge during climbs. Even fuel efficiency showed marginal improvement because engines didn't have to work as hard to maintain speed when tracks weren't constantly breaking through surface crusts. Not every aspect of the modification was positive. The extended end connectors added approximately 300 pounds of steel to each tank, most of it at the periphery where it increased rotational inertia. This made steering slightly more sluggish and increased wear on the tank's controlled differential and final drives. Maintenance crews reported increased track tension adjustments required because the longer track runs stretched differently under load. The extensions were also fragile when tanks operated on hard surfaces. Concrete roads, stone bridges, and rocky terrain could shear off extended end connectors that struck obstacles at speed. Crews learned to be cautious when transitioning from soft to hard ground, and some units developed procedures for removing the extensions before road marches and reinstalling them before cross-country operations. But these were acceptable trade-offs given the alternative. A slightly slower turning radius was infinitely preferable to being stuck immobile in mud. Increased final drive wear was manageable with proper maintenance. Occasional broken extensions could be replaced quickly. The modification wasn't perfect, but it worked, and in combat that was sufficient. By February 1945, as Allied forces pushed across the Rhine and into Germany itself, extended end connectors had become so standard that their presence was unremarkable. Combat photographs from the final months of the war show Shermans with the distinctive protruding track extensions in virtually every image. Veterans' accounts mention them casually if at all, because they'd become just another part of the tank, no more noteworthy than the main gun or hull armor. This normalization represented the ultimate success of the modification. Something that had been unauthorized and controversial in October had become completely routine by February. The army had absorbed a bottom-up innovation so thoroughly that it became invisible, just part of how Shermans were equipped for European combat. The official Ordnance Department response to extended end connectors evolved from resistance to grudging acceptance to retroactive embrace. Initial reports from October and November 1944 show clear bureaucratic frustration. Staff officers in Paris complained about non-standard modifications complicating maintenance planning. Engineers at Aberdeen Proving Ground questioned whether field-welded extensions would maintain structural integrity. Procurement officers worried about establishing precedents for unauthorized equipment changes. All of these concerns were legitimate from the perspective of military institutional management. Standardization exists for good reasons. Quality control matters. Maintaining clear chains of authority for equipment modification prevents chaos. The Ordnance Department wasn't wrong to be concerned about field units making unauthorized changes, but the department was wrong about priorities. In the hierarchy of concerns, preventing unauthorized modifications should have ranked below keeping tanks mobile and crews alive. The Ordnance Department initially treated extended end connectors as a procedural problem when it was actually a survival solution. This disconnect revealed the eternal tension between bureaucracy and battlefield necessity. The shift in official attitude became apparent in January 1945, when ordnance officers began quietly facilitating rather than obstructing the modification. Steel supplies were redirected to maintenance units, known to be fabricating extended-end connectors. French contractors received tacit approval for their production efforts. Quality standards were informally communicated, even though the modification remained officially unauthorized. This represented institutional flexibility that deserves recognition. The Ordnance Department could have rigidly enforced regulations and ordered removal of all unauthorized modifications. Some staff officers argued for exactly this approach, but senior leadership chose pragmatism over procedural purity. They recognized that combat effectiveness mattered more than regulatory compliance. The formal authorization in March 1945 came with detailed specifications that revealed how thoroughly the Ordnance Department had studied the field modifications. The official technical manual specified exact dimensions, materials, welding procedures, and installation protocols. Much of this specification was simply codifying what experienced maintenance crews had already discovered through practical experience. One notable aspect of the official specifications was their flexibility. Rather than mandating a single rigid design, the manual provided acceptable ranges for dimensions and materials. This acknowledged the reality that combat theaters operated with whatever resources were available. The specifications ensured minimum quality standards while permitting the adaptability that made extended-end connectors successful in the first place. The manual also included an unusual historical note crediting field maintenance personnel for developing and implementing the modification in response to operational necessity. This represented remarkable institutional humility. The Ordnance Department was officially acknowledging that its own engineers hadn't solved a critical problem, but anonymous mechanics had. That acknowledgement would influence post-war thinking about military innovation and the role of field-level initiative. The long-term impact of extended-end connectors extended far beyond their immediate tactical value. The modification established a template for rapid field innovation that would influence American military practice for decades. It demonstrated that combat effectiveness could be improved dramatically through simple modifications, implemented quickly, without waiting for official development programs. The Korean War saw similar patterns. When American armor struggled with Korean terrain, maintenance units developed field modifications without waiting for approval from stateside engineering centers. The modifications to M4 Shermans and early M26 Pershings used in Korea bore clear conceptual lineage to extended-end connectors, same philosophy of local improvisation addressing immediate problems. Vietnam continued the tradition. Gun trucks, improvised armored vehicles created by mechanics welding steel plate onto standard trucks, represented exactly the same approach. Unauthorized modification driven by necessity, spreading through informal networks, eventually receiving grudging official acceptance. The institutional memory of extended-end connectors provided cultural permission for these later innovations. Modern American military doctrine now explicitly incorporates rapid fielding initiatives and theater-specific modifications as recognized and valued practices. The Marine Corps established its urgent universal need statement process. The Army created rapid equipping force structures. These formal programs exist partly because extended-end connectors demonstrated that bottom-up innovation could be more responsive than top-down development. The modification also influenced tank design philosophy. Post-war American tanks consistently featured lower ground pressure and wider tracks than their World War II predecessors. Engineers recognized that mobility in varied terrain conditions was sufficiently important to justify design trade-offs. The M46, M47, M48, and eventually M60 tanks all incorporated lessons learned from watching Sherman struggle in Belgian mud. Even modern main battle tanks like the M1 Abrams show this influence. The Abrams was designed from the start with extremely low ground pressure, approximately 13 psi for a tank weighing over 60 tons. This was achieved through very wide tracks and distributed weight, precisely addressing the problems that had made extended-end connectors necessary 40 years earlier. The Israeli experience with Sherman tanks provides a fascinating postscript to the extended-end connector story. Israel operated Shermans extensively from the 1940s through the 1970s, long after they'd been retired from American service. Israeli armor units fighting in desert conditions faced different terrain challenges than European mud, but encountered similar ground pressure issues. Israeli mechanics, many of whom had learned their craft in British or American service during World War II, knew about extended end connectors. They adapted the concept for desert operations, developing grouser attachments that improved traction in sand while maintaining mobility. These Israeli modifications, in turn, influenced American desert warfare preparations and eventually fed into M1 Abrams design requirements for operations in Middle Eastern terrain. The circle of influence extended to other nations' armor development. British Centurion tanks featured wide tracks, partly because British observers had noted Sherman mobility problems in Europe. Soviet T-54 and T-55 tanks incorporated similar lessons. German Leopard tank design emphasized low ground pressure explicitly. The simple field modification of extended end connectors contributed to how virtually every post-war tank designer thought about mobility. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The final assessment of extended end connectors must acknowledge both their immediate tactical impact and their broader institutional significance. In pure military terms, they improved Sherman mobility in soft terrain by approximately 30 to 40%, reduced losses due to immobilization by estimated 40 to 50% in affected units, and contributed materially to sustaining Allied offensive operations during the critical winter of 1944 through 1945. But the deeper importance lies in what the modification revealed about military innovation. It demonstrated that effective solutions to combat problems could emerge from any level of the organization, not just from credentialed experts in official laboratories. It showed that speed of implementation often mattered more than perfection of design. It proved that survival imperatives could and should override procedural regulations. The mechanics who welded steel plates onto track connectors in November 1944 weren't trying to make institutional statements or revolutionize military procurement. They were trying to keep their friends alive, but in solving that immediate problem through unauthorized innovation, they established principles that would influence how militaries approach adaptation and field modification for generations. The extended end connector was never glamorous. It didn't have the dramatic appeal of the Cullen hedgerow cutter or the technological sophistication of radar-directed anti-aircraft guns. It was just wider tracks, achieved through the simplest possible means. But those wider tracks kept Shermans moving when they would have been stuck. They kept crews alive when they would have burned. They sustained offensive momentum when it would have stalled. In the end, extended end connectors saved thousands of American lives and materially contributed to ending the war in Europe months sooner than might otherwise have been possible. They achieved this not through advanced engineering or massive industrial programs, but through the initiative of mechanics who refused to accept that men should die because regulations forbade simple solutions. That refusal to accept unnecessary death, that willingness to break rules when rules conflicted with survival, that confidence that field-level personnel could solve problems that baffled official experts, these represent the best traditions of American military culture. Extended end connectors embodied those traditions in 4 inches of welded steel. Unpretentious, practical, effective, just like the mechanics who created them.